In this section, we're going to continue with our discussion on probability, and we're going to focus on a new area regarding joint events. And we'll also be talking about the complement of events. The joint event is going to be a situation like red and ace from a poker card deck of 52 cards. Well, there's two red aces, so it's a situation that's defined by this sort of a probability, 2 out of 52. The complement of events are sort of the opposite. It's all cards except the red aces out of a poker deck. So in this example, it would be the 50 remaining cards that are not red aces divided by 52. Both of these concepts are going to be helpful to us as we move forward with these examples. Just keep these simple illustrations in mind. So joint events, this is all about the union of two things happening. A union, a tip that we're looking at as a union is a business question like this. What's the probability that someone is a top customer, a best customer, something like that, or male? So this is really describing the language here is the union of two events. Now you might intuit this, sort of get a picture in your mind of thinking about all the different customers that you might have, and then you can imagine some of them are male and some of them are female. And this question is asking you if you had to go out and select among them some random person, what's the likelihood, what's the probability that you're going to select someone who's a top customer or somebody who's male? So one way of looking at a question like this is in a table. These tables are a very intuitive way of sort of looking at the entire landscape of possible options. We know these to be sort of events of effectively an experiment for probability. So here I have 50 customers in total. And of those 50 customers, some are male and some are female. In fact, I see I have 26 males, 24 females. And then some of them are top customers and some are not top customers. So I have 16 top customers and 34 not top customers. So these are very helpful tables to sort of intuit overall. These are known as marginal probabilities or totals. And then we have the actual events or observations that are in the middle for. But let's continue on with our example. How would I figure out what the probability is for someone to be a top customer or male? So this is written here this way. The probability of being a top customer is 16 out of 50. Well, I can see that. I had 16 customers out of 50. So the probability is going to be 0.32. Then the probability of them being male, well, that was 26 out of 50. And so intuitively, it's very simple. Now, what might not be so intuitive is that the next step of this equation. This is known as the intersection of these two events. And I've highlighted in green here where the numbers are coming from. So it almost pops out at you that the 6 that are in this cell were actually, in a way, counted twice. They were first counted as part of my top customers in blue, and then they were also counted as being male in green. And so the formula for the union of two events reminds us of that. We've got to subtract that out. So 6 out of the 50 have really already been double counted. So by subtracting that out, I can finally get to the correct answer here. The probability that someone is a top customer or male is 0.72, or in other words, there's a 72% chance of randomly selecting a top customer or a male. And again, I think that the table sort of intuitively shows you that, and the intersection really pops out here, and that's why the formula helps us subtract that away, because we've really double counted it being both in green and in blue. We'll come back to this concept as we progress. So the probability of the union of the top customer or male is written this way. You'll see the nomenclature this way, this is the probability of a top customer union male is the probability of a top customer plus the probability of male minus the probability of a top customer intersection male. I know that's a lot of verbiage. I think the most important thing is intuitively understanding how we're getting to the probability of 0.72. And then we're not double counting the intersection where someone is both a male and a top customer. We only need to be including in that probability estimate one time. And so you'll definitely help yourself and your peers understand probability by taking that out. So that's the takeaway there. Now, the addition law of events is a situation that we're talking about here where really we're looking at event A or B or both occurring. That's what the addition law is helping us intuit. What's the probability that someone is a top customer or male? That's really the situation that we were just looking at a moment ago. And we saw clearly the probability of being a top customer is this 16 out of 50, 16 out of 50.32. And the probability of being male is 26 out of 50, that 0.52. But we had to subtract out the bottom half, and this was the intersection. So I'm just making it very, very clear that this is in the terminology called the intersection and how we interpret this part of the actual formula. All right, so let's move on with another example here. Just to complete this, the addition law provides us a way to compute the probability of event A, event B, or both, A and B occurring. The formula is written as we've just discussed in the prior slide. So now moving on, another interesting thing that is very intuitive in the table is this sort of a situation. I'm asking the same question here. What's the probability that someone is a top customer or is male? But something is very unique. Something has happened that's a bit different here. You can see from the table that I can see the males and I can see the top customers, but there's actually no cases, there's no observations, there's no occurrences of the two occurring together. So in that situation, when we add up the probability of a top customer, which is 10 out of 50, and the probability of being male, the 26 out of 50, 0.2 and 0.52 respectively, we can see that the probability is actually the same as what we saw in the prior example, but in this time, the intersection is actually 0. There's no cases of a top male intersecting with a top customer, rather, intersecting with male, and so 0 out of 50. Whenever you take the intersection of two events and you come up with 0, that's an indication that they are what's called mutually exclusive events. A mutually exclusive event will have no intersection. So the event of being a top customer and the event of being a male are mutually exclusive to each other. I won't find any cases, and you can see that in the table. I have no cases of the two combined. So if I'm a male, I'm definitely not a top customer. And if I'm a top customer, I'm definitely a female. And that's another way of thinking about your market. The addition law provides a way of computing that. We use the same formula. The unique thing that's happening here is if you come up with the intersection of 0, it's telling you the events are mutually exclusive. The conditional probability is another situation. What if the outcome of one event is influenced by another event that's already happened? We see this in business all the time. Take this situation right here. A customer makes a purchase of a new event after obtaining a discount coupon, which is the first event. So, intuitively, I might want to know, is this new purchase, this new event, occurring after they've received my promotion? This is really important as a marketer. It would be really good ROI to know that my first event was a discount coupon that was maybe associated with the new event of the purchase. It might make me feel better that my marketing dollars are being well spent. So knowing the probability of the first event can actually influence the probability of a new event. In this case, it's the sale. First event was a promotion. Second event's the actual purchasing of something by the customer. This is a conditional probability. We know that it's a conditional probability by the clue, often by the word given. The probability of an event given the status of another event is a conditional probability. So in the language probability, you'll see this a lot. Note that the conditional probabilities are telling us that there's some kind of interaction between two events. And that's really important information for us to know in business, that two things are somehow related. Conditional probabilities going on is this sort of nomenclature written out this way. The conditional probability of A given B has already occurred is denoted by this notation here. The probability of A given B, that up and down line there is interpreted as given. So what's the probability of A given B? It's the same thing as saying what's the probability that one of my top customers is given that the customer is male. So again, what's the probability that this is one of my top customers given that they are male? I think we'd all agree that it's important to understand that male probably came first. The person was born, the person has sex. So given that the person's male, are they my top customer? The conditional probability can be computed in this way. Conditional probability of a top customer given that they are male. This is found by looking at the probability of the intersection that we saw in the prior example of these two events. Just imagine what that would look like in a table, the upper left-hand corner in the prior example. And then you divide that by the probability of, in this case, male. You're always going to be dividing by the denominator will always be given whatever it is you were given information about. That's the denominator. So let's look at this example. I think that makes it a little clearer. Here's our table again. And we know we're doing something unique or special again with this upper cell. What's the probability that someone is a top customer up here, given that they are male? So again, I think it's really helpful to see this in a table. A top customer, and we also have some non-top customers here. We'll come back and look at what that looks like when we could ask a question about non-top customers. But the probability that they're a top customer given male, here's our formula. You have to find the intersection of A and B, which we actually had done that in a prior example. And then we're going to divide that by the probability of B. Well, we know the probability of that is going to be something to do with the 50. So here is this written out. The probability of top customer, this is talking about the intersection. The probability of the top customer intersection male is 6 out of 50, which is the 0.12. And then we have to divide that by the 26 out of 50, because the 26 out of 50 is the total probability of being male in my whole sample. So here's it is written out, and then I divide those probabilities up, and I can see, here's what I've written out in words. I'm first getting the probability of top customer overall, males, and then get the probability of males overall and just divide those up. That's exactly what we've done here in the formula. So here's an interpretation there. I now know that the intersection of a top customer given that they're a male, someone is a top customer given that they're male, is 0.23. Or in other words, if I were to go in and select at random someone from the whole sample, I'd have a 23% chance of finding someone that is a top customer given that they're male, because I'm really actually only looking at this column. I was given the information ahead of time that they're male, and so I'm only really dealing with this 26 out of 50. That's really helpful, actually, to narrow that down. Now, the multiplication law for the union of events is used also in conditional probabilities, but it's read a little bit different. Notice here, we're not given anything. What's the probability that someone is both male and top customer? Notice here, nobody said anything about given. So I'm no longer dealing with just this column of data. I'm going to have to deal with the entire set of data. So what's that probability? What does that look like? How can we use this new rule? Well, the nomenclature for this, the way that I write this out, is the probability of male. We've actually figured this out before. It's 26 out of 50. There's our 52. We looked at this earlier. 26 out of 50 is the probability in the sample of being male, not female. And the total probability of being a top customer given male, we had seen that earlier. We know that is 0.23. We just calculated that in a prior slide. But what's interesting now is this is a new way of looking at the intersection. So the probability of being a top customer intersection male, you can multiply these two things together. 0.52 and 0.23 is the 0.12. Now, some of you are going to say, wow, that was a lot of work to get to something that I could really intuitively see. The 6 out of 50 was the same calculation that we got earlier. It gave us, I think, the same value as the intersection. The probability that someone is a male and is a top customer is 0.12, or 12%. 12% chance to randomly select a male customer that is a top customer. We can see that. And so I'm agreeing with you that this is, if you intuitively could see that in the table, you could immediately interpret that your top customers were 0.12 or 12% of the overall sample. That puts you ahead of the game. That will make you, a hit in your next staff meeting. But some of us need to work this out, and as the examples get more complicated, it's helpful to have a mathematical way to look at it. So the multiplication law provides a way of computing the probability of event A and B occurring. The formula is written out here. So here's the intersection, probability of A intersection B is equivalent to the probability of A times probability of B given probability of A. So that's the way that it's read, but I think intuitively you can see above from the example that we just worked, it's a little bit easier to understand it in words and using the table to understand. And it is the same calculation for the intersection that we completed just a few slides ago, as I've already mentioned. All right, now a little bit more on conditional probabilities. What's the probability of somebody that is a top customer given that the customer is not male? Well, obviously, if they're not male, they have to be female. So the point is you can use the same information and sometimes you'll see the little caret above whatever it is the notation is. In this case, it's the probability of being a top customer given not male, in other words, female. And it works the same way. Well, we can see here the probability of being a top customer given that they are not male, female, is 10 out of 24, because I'm just going to be working with this column of data here, given that they are not male. So there it is, 0.42. Now, let's put these two ideas together, because this is where it gets a little interesting. We can actually detect what's known as dependent events based on the outcome of these two analyses. A dependent event is really helpful to us in business because it might help me decide what kind of budget I put to marketing to certain customers, for example. Or if these were product defects, it could also help me decide where I need to put money to fix a problem. Let's continue on with this example of top customers and see how that works. We already looked at the probability of being a top customer given that they are male is 0.23 or 23%. And we also looked at the probability of being a top customer given not male. And we just saw that for females is 0.42. Well, what does that all mean? Well, if we know that a customer is male, the probability of him being a top customer is only 0.23. However, now we can see that if a customer is female, the probability of them being a top customer is 0.42. Well, that's nearly double. So knowing that a customer's sex, either male or female, tells me a great deal about how good a customer they are. I would definitely in this situation recommend that we spend more time, effort, energy marketing to our females and maybe seeing how we can grow this relative to males. Or if we wanted to convert more males to be top customers, now we know we have quite a big a road to double effectively the likelihood that they're going to be a top customer, because right now females are definitely winning. This shows that customer type and customer sex are known as dependent events. It's dependent because knowing something about a customer's sex helps me interpret and understand whether or not they're a top customer. I can definitely see that from the calculations. I had nearly double the chance to select a female at random. And that definitely tells me that I want to focus on them. And they're dependent. I found something out about the customer's sex, and it tells me about the customer type that they are. Now, to contrast that, two events are independent if the probability of one is not changed by the existence of the other. So this is really a whole different situation than what we have here. For independent events, the probability of event A is not changed by the existence of event B. Let's illustrate that with a common example. Let's go back to a deck of regular poker cards, 52 cards in the deck. Now, two events are going to be independent if the probability of one is not changed by the existence of the other. The probability of event A is not changed by the existence then of event B. That's an independent situation. It's written this way. This is the formula here. Probability of A given B is going to be the same as probability of A. Well, obviously, if you think about this long enough, and I'll illustrate this, despite how convoluted the language is, this is very intuitive. Knowing information about event B has no effect on the probability of event A. It would be very much like this sort of a situation here. What is the probability of selecting an ace from a deck of poker cards, given that the card is red? My question is, are these independent events? That's the question I want to find out as well. So let's look this over here. Here's what that would actually look like, and let's walk this through. First of all, I want to find out what is the probability of an ace given that it's red. Well, I was given only the red cards here. That's really helpful to know. I'm only going to be looking at red cards. Well, I know there's 2 red aces, so 2 out of the 26 would look like this. The probability is 0.077. So the probability of selecting a ace from a deck of cards given that they are all red is that's a typo. That it should be 0.07. 0.07. I'll have to correct that on the deck that I give to you. And also, what is the probability now of selecting an ace given all the cards? Well, the probability of an ace is 4 out of 52. So 4 out of 52 is the same. So if I'm looking at all the cards here and I'm not given any, 4 out of 52 is the same probability as 2 out of 26. When that happens, we say that these are independent events. The way that I like to think about this is that there's really no information gained. So if there's no information gained, we have 2 independent events. We don't know that the card is red. It would just be the same probability of selecting an ace overall. If we're not given any information over here, selecting 2 red aces given just red cards are the same as selecting any ace out of all the cards. So these events are independent. The probability of selecting an ace given only red cards is equivalent to the probability of selecting an ace given all the cards. So that's how you would know you have independent events. Now, the union of events are something really practical that you can use to help you make decisions as a manager. Here's an example. Marketing manager tells you 2 promotional campaigns are about to launch. The first promotional campaign is targeting to customers 35 years old and older, and then a second promotion is going to target customers 44 years old and younger than that. What's the probability that customers are going to get one of the promotions? Well, it looks something like this. Promotion A is targeting customers 35 years old and older. So that's definitely down here, 35 years old and older. And then promotion B is targeting customers that are 44 years old and younger. So how would I figure out what the probability is that they're going to be getting a promotion? Well, let's use the addition rule that we learned. Probability of A is going to be the sum of all of their probabilities. So here is A's promotion. I can start here at 0.20 for 35 to 44-year-olds, 0.10 for the next segment, 0.05, 0.05, and that adds up to 0.40. So if that was the promotion of all the customers, there's effectively 40% chance that I'm going to, using the relative frequency method, that they're going to receive that promotion. Now let's do the same thing for promotion B. What's the probability that my customer segment's going to get promotion B, given that it's targeting people that are 44 years and younger? Well, this is the number of them in the sample. I'm going to use this relative frequency to help me out. So 0.20, 0.30, 0.20, 0.10. And that's telling me that, well, there's effectively 80% of my customers are likely to see promotion B. So this might be very exciting to you, but you also need to understand we're not quite done. We have to add up these two, 0.40 and 0.80. Wait a second here. I thought that we said earlier that probabilities always sum to 1.0. I mean, we can't have more than 100%. So what's going on here? Well, it can't actually be 120%. 120% of my customers doesn't make any sense. 120% couldn't possibly, see it all. Now, what's happened here is we've double counted, just like in the contingency table that I looked at earlier. We've actually double counted the 20%, because this segment is actually possible for them to see the first promotion A and the second promotion B. And so I've double counted them accidentally as I worked through this example here. And if you remember in the addition rule, the addition law says we've got to take out the double count. And so the probability of them getting a promotion, P, is going to be the 0.40 and the 0.80 we just calculated, but we have to subtract out the overlap. And again, when you saw it in the table, it probably jumped right out at you, but oftentimes as managers, we're looking at things in meetings and people are talking about the likelihood of events or the probability of events, and it's not always intuitive that there's some overlap. And you could get somebody interpreting something that is as silly as saying 120% are going to be receiving something, and that's not exactly true. A more correct way of saying it is that 100% chance of customers getting a promotion, either A or B or both. And indeed, this segment is likely to receive both, but you can't exceed more than 100% chance of anything happening. There's a 100% chance that all of our customer segments will receive the promotion. All right. We can also use this sort of a layout to look at mutually exclusive events, which we also looked at in the table, but here's another way of looking at it. If promotion A is targeting customers 55 years and older, and promotion B is targeting customers 25 years and younger, or under 25, so 24 and younger, then we can see here that there's, through the probabilities, we're just going to add those up. So we start with the segment of 0.10 and 0.20 for probability B and A, the respective 0.5 and 0.05, 0.05. And then using the additions law, we can just add that up and we can say, well, the probability of a promotion reaching those segments are the 0.10 and 0.30, so 40% chance. And we know that they are mutually exclusive because there's no intersection. Obviously, there's no overlap here. And we said earlier when we had that happening, we can interpret it as mutually exclusive events. In other words, the promotion A is mutually exclusive to people 55 years and older, and promotion B is going to be exclusive to people that are 24 years and younger. One way that I have found helpful is to try to put the keywords in some kind of a cheat sheet for myself when I'm thinking about probability. I might be looking at a table of some kind about what do I want to see. And here are some, 3 different ways to sort of interpret that and then guide yourself to the appropriate way of calculating that. If I want to see the probability of A or B or both, then the addition law is appropriate. So this is a situation where I want to know whether I have top customers or male or both in my store, and so here this works even if they are mutually exclusive, and you'll know they're mutually exclusive when there's no events in that intersection, which is this part right here. Now, another situation is I want to see the probability of A given B. I'd like to know what the probability of my top customers given that they are male, for example, as we saw in the example. This is conditional probability. Find the intersection of the events and divide the probability you were given the information about. So remember, the probability of top customer given male is the intersection of top customer and male. In our table, it makes that really easy to see, divided by the total probability of just being a male in the sample. And so this is one way to use the conditional probability to figure that out. Now, the third case is I want to find the probability of both A and B. So here, I'm not given any information, and I want to know a joint event that's happening. So here I can use the multiplication law. Find the probability of A, find the probability of B given A, and then multiply the 2 probabilities together. So this is the same as calculating the intersection, the probability of a top customer intersected with being male. And we can do that mathematically by looking at the probability of top customer, probability of male given their top customer. And this would be the same thing as, hopefully in the table that's going to pop right out to you and you won't need to use the formula, but just in case, it's good to have the formula and you can understand how to back into that. So what's the takeaway from the 3 sessions that we had? Well, we looked at 3 different settings for probability. The first setting was a simple question of how many sales will I make from the next 4 customers? And for that, we are using experimental outcomes that could happen totally by chance. And for that, we could use the product rule, the combinations rule, or the permutations rule. All of these are classical methods for us to just assume that events are equally likely and what would happen if. And this is thinking about it as flipping a coin or rolling a die. The next sort of questions we started to ask were a little bit more sophisticated. How likely is it that each of my customer segments will make a purchase this month? Or what's the chance that I need more stock on hand? For those kinds of questions, we can use the relative frequency method or the subjective method. As you're becoming familiar with your business, you likely could estimate the probability of things happening. And knowing that and knowing the total of some things, you can actually figure out what the level of stock you might need, or from the level of stock that you have from a total sold, you can figure out the probability of different segments or different combinations of things happening. So very useful to look at budgeting or decide whether you need to put more attention on something. The last case we looked at is, what are the chances that my marketing promotion will reach new, say, female customers? So this is the kind of question where I'm trying to figure out, an event that's a combination of things. I have new customers and I have female customers in this example. So for that, these are joint events. We can use the addition law if it's a union. We can use the multiplication law for the intersections of events. Or if we are given some information, such as we're just going to be looking at marketing promotion given that it's only going to female customers, that's very helpful information that can help me look at the probabilities a little bit more directly. And so we would use the conditional probability and multiplication laws for that. So this is a summary of probability. I hope that is making some sense, and you'll find some practical applications for that in your day-to-day management responsibilities going forward.